Hey everyone, how's it going? I thought I'd work through problem 16 of chapter 15.4 in our textbook by Larson and Edwards for this Multivariable Calculus course. I chose this problem because it's from one of the more involved units of this course. It's been one of the most difficult units for me so far, at least. And so we see that we're integrating over our contour gamma the integrand 2 arctan y over x dx plus natural log x squared plus y squared dy, where gamma is the contour that's parametrized by our functions of x and y here in terms of theta, which trace the counterclockwise oriented ellipse in the plane. So we see by the equations that they provide, the derivations that they provide on page 1077 in the textbook, that we can rewrite one as this integral. And we see in the differential, what we're integrating with respect to actually becomes the contour by substitution. So this reminds me a lot of Riemann-Stieltjes integrals, which you can read about in texts like Witter's Advanced Calculus and stuff. But it's just analogous because we can take the vector out of the differential by taking the derivative of it, and if we treated this Leibniz notation, d theta and d theta, as fractions, we'd see that the d thetas actually cancel. Although, of course, that requires a few intricate things that you can read about online. But we'd be left with the d vector, basically. So another thing I could have done is change this contour gamma to the limits that we're integrating over with respect to theta, because now we're integrating with respect to theta instead of over our contour. So we're transforming our contour integral into a Riemann integral that we'd normally see. So here I've rewritten the integrand in terms of column vectors. So we have 2 arctan 4 plus sine theta over 4 plus 2 cos theta in the x component. And in the y component of our vector field, we have the natural log of 4 plus 2 cos theta squared plus 4 plus sine theta squared. And the whole thing is dotted by the derivative of our contour. And in 5, I've just written it all out, the dot product. In 6 and 7, I've rewritten the integral so that we can see the whole thing, and I've changed the limits of integration from 0 to 2 pi because, as I said before, it's a counterclockwise oriented ellipse, so we're integrating over 360 degrees. Now to see that it's an ellipse. So the contour gamma, it's parametrized by our functions of x and y here in terms of theta, and by subtracting the 4 and dividing by 2 and then squaring, we see that x minus 4 over 2 squared is equal to cosine squared of theta. And the same thing is done for y. Now, by the Pythagorean trigonometric identity, we can, such that sine squared of theta plus cosine squared of theta equals 1, which is one of the most common trigonometric identities in all of mathematics, we see that we have the equation of an ellipse that's centered at 4, 4. This is because x minus 4 and y minus 4 move it to the right 4 units and then up 4 units. And in the x direction, we are dividing by 2, so we have a semi-major axis in the x direction that's twice as long as the semi-minor axis in the y direction. And we can see that in the graph here. I've overlaid in Mathematica the path of our ellipse, the contour that we're integrating over, in the vector field, which is all the arrows here. And so we see the ellipse is centered at 4, 4. We have 1 unit and 1 unit and semi-major axes in the y direction, and 2 units in the x direction are semi-major axes. And Green's theorem. Now we can look at Green's theorem because we know our contour is a closed contour. It doesn't contain any asymptotes or singularities, so we don't have to dodge them or anything. But we can use Green's theorem, and we see that the integral over the boundary of this region, which is our contour gamma, of the vector field dotted with the differential, which contains the vector the vector, the parametrized contour that we're traveling over, that we're traversing in the integral, it's equal to the double integral of this region contained within the contour of the curl of our vector field dotted with the k basis. And this is also equal to the double integral of our second mixed partials of the potential function, if there exists one. Another thing to note is that since our curl of our vector field is equal to nabla crossed with our vector field, it's equal to the determinant. So we can flip this side or flip this side, it doesn't matter, but we always end up with, well, in this case, we're ending up with the k component because the x component and the y component don't exist. Yeah, they disappear from the determinant, so we can see that in the textbook they actually write it out so that we can see that they disappear. So for the I component, we would have we'd only have partial 2f, partial y, partial z, and in the j component we'd have partial 2f, partial x, partial y. But in the k component we would have partial 2y, partial 2f, partial x, partial y, minus partial 2f, partial x, partial y. So now we can just look at our vector field, and we can take the partials as we would do in number 15 here, and we see that they end up being equal to one another. So in their difference in the integrand of our Green's theorem, they equal 0. So the contour integral should equal 0. If you look at the textbook, actually, see, I mentioned down here there's another example page on page 1095 of our textbook. The contour integral over a conservative vector field that is closed and ends up back at it traverses some distance, but it always ends up back at itself. There is 0 work that's done. So if we take an object and we move it throughout a conservative vector field, we could move it 100,000 units up and 250,000 units along x squared to the left or something like that, something crazy. But as long as we come back and we don't traverse any singularities, we dodge all of those things, we should have 0 work done. That's my interpretation of what this theorem is saying. So since it's a closed contour, we can write it as an OInt. In LaTeX, the command is /OInt. Over our contour gamma, the boundary of our region R here for Green's theorem, of our integrand is going to equal 0. So really interesting problem how it all worked out and just ended up equaling 0.